In the first two labs of this semester, we're going to deal a lot with electric forces, although indirectly, and then also fields and potential. In fact, in the lecture, at least for Physics 102, you'll see that these are in chapters 1 and 2, and they're very important chapters that will lead into other chapters. The idea of an electric force, an electric field, and electric potential. And so you have the great opportunity to learn about all three of these just on this very first lab day. You remember back in first semester physics when we talked about the gravitational forces between masses, we said that there is a if I have two masses that are separated by a distance, say r, that the force between them, which is going to be an attractive force, is equal to g, which is some constant, times the two masses, the product of the two masses, divided by r squared. That was called Newton's universal law of gravitation. Now, we're going to see something very similar in Coulomb's law, because the gravitational force and the electric force are both spherically symmetric. They have the same mathematical form, and so they'll look very similar. Here, this is the expression of Coulomb's law, and it's basically the same as Newton's universal law of gravitation, where I have two charges, Q1, Q2, and they're separated by a distance r, and the force is given by this equation. Now here, this is a constant, which is kind of akin to the gravitational constant, not the same, of course, but akin to it, analogous to it. And this, we're going to use the symbol k, 1 over 4 pi epsilon naught. So that is our symbol k, is our Coulomb's constant, we'll call it. If you have more charge, you'll have a stronger force, and then just as we saw with the gravitational force, if I separate them, then that force will become weaker. And then the force is also dependent upon the permittivity of the medium, which is given by this 8.85 times 10 to the minus 12. Now, we'll see that K is equal to 9 times 10 to the 9th. Although you don't need that right now, we'll see that later. Let's see, the units for K would be Newton meter squared per Coulomb squared. Okay? Now, electric fields. Fields might seem kind of strange to you, but we've already seen fields in the first semester, but we didn't call it a field. We dealt in the first semester with something called gravitational fields. I tricked you, though, because never talked about it. I think you never called it this, because you know I'm a tricky guy. But the gravitational field is g. Remember the acceleration due to gravity? That is a measure of the gravitational field. That g is equal to F divided by m. Remember, this comes from F equals ma, or F equals mg. That's Newton's second law. So the gravitational field, or the acceleration due to gravity, is the force per unit mass. In a very similar way, the electric field is going to be a force per unit charge. The electric field can be represented graphically by lines of force, or we're going to call them actually electric field lines, with the same direction as the field. So a couple of rules about these lines of force. The number of lines per unit area represents the magnitude of the force. So let's say that I have a positive charge. The way that I determine the electric field is I'm going to take an imaginary charge that's positive. So this is my imaginary positive test charge. A positive test charge. And it'll become really important in the lecture as we think about electric fields and mapping out electric fields. So the way that I determine the direction of the electric field is I ask, what is the direction of the force on this positive test charge? Now I know that like charges repel one another, so the force on that positive test charge due to this charge is away from the original charge. Then the direction of the force is the same direction as the electric field. So my electric field is going to be in that direction. Likewise, if I put my positive test charge over here, I will see that there's a force in that direction and an electric field in that direction. I can do that all around. Now, the positive test charge is imaginary. It doesn't actually exist. I'm just using it in my mind to map out what is the electric field surrounding this positive charge. Now, what would happen if I have a negative charge? Well, I put my little positive test charge right here. I say the force is going to be in that direction, so my electric field is going to be in that direction. So those are two very simple electric field maps for a positive charge and a negative charge. Notice that, let's look at my rule here. The number of lines per unit area represents the magnitude of the force or the magnitude of the field. What that means is if the lines are closer together as they are here, I have a big electric field. But if the lines are far apart, as they are out here, I have a small electric field. The number of lines per unit area, the line density, represents the magnitude of the force. And then also, the lines give the direction of the field, the force lines. Okay, so here's my single positive test charge right here. The lines are directed radially outward. I indicated that my positive test charge is going to move away, and then I also did it for the negative charge there. Now, as I have a charge moving through an electric field, it can require a certain amount of work in order to move that charge through a field, through a changing electric field. And the way that we're going to describe that work is through something called potential. Now, potential, let's think back here. So I have my force is KQQ over R squared. My electric field is going to be a force per unit charge. So that's going to be KQQ over R squared divided by Q, or KQ over R squared. That is my electric field. It is a Newton per Coulomb, or a force per charge. The force is newtons. And now my voltage, or my potential, I'm going to use those words sort of interchangeably. We'll see later in a chapter that there is a little bit of difference, but my voltage or electric potential, that this is a measure of energy per charge. So whereas the electric field was a force per charge, my potential is energy per charge. And of course, by the work energy theorem, we can also say that this is a work per unit charge. And then force, of course, is just a force. So we have this progression from our electric force to our electric potential to our voltage, from our force to our electric field here to our electric potential or voltage. And this voltage is equal to work divided by Q, or energy divided by Q, and it is the work as I move from one point to another, as I move from, say, point A to point B, as I move a charge from one point to another. That voltage, or that potential, is the quotient of W over Q. And then I can also, since I know that work is equal to force times some distance, I can say that our voltage is equal to my force, which is KQQ over R squared, times some distance, which I'm just going to say that's in R, divided by Q, gives me an expression for voltage, which is KQ over R. So now I have an expression for my electric field, my electric force, and my electric potential. That's not terribly important for this lab, but it is really, really important for the class. So I want to go ahead and put that out there for you. That I have these three big ideas: force, fields, and potentials, and they're all dependent upon either the force per unit charge, or the energy per unit charge. The potential is the same at all points at a distance RA. Listen, that's just saying that if this is constant, then the potential is the same. So let me draw my positive charge. These are my field lines, as we've already seen. I'll do the potentials in red. So if this is a distance R, my potential is V. If this is a dimensional R, my potential is V. And actually, I'm going to put a V1 on there. This is also V1, and this is also V1. Likewise, all along here, at a line that is the same distance from that charge, the potential is always the same. This is called an equal potential line. Along that line, the potential is always the same. So let's say, for example, the potential here is 4 volts, or 4 joules per Coulomb. Those are the SI units for voltage, joules per Coulomb, or volts. Then over here is going to be 4 volts, over here 4 volts, and over here 4 volts. Now I can draw another equipotential line, say right here. Let me ask you the question, is my voltage now bigger or smaller than it was before? Oh, well, my distance is smaller, so this has gone down. That means that my voltage has gone up. And it looks like the way I've drawn it, my distance has gone down by a factor of 2. So I would say then that this is going to be 8 volts along that equipotential line. Because I've decreased my distance by a factor of 2, that's going to increase my voltage by a factor of 2. As I get closer to that charge, then my energy per charge will increase. All right, and then likewise I can have an equipotential line out there. Equipotential lines, notice, are always perpendicular. They're always perpendicular to the field lines. They're perpendicular there, they're perpendicular there. And that's all. Okay, so next we'll get into the procedure. I'll show you how to use the FET.